Have you wasted hours playing with Craiyon yet? It's free, it's easy, and it's fun. Text to image models like Craiyon, Midjourney, and Dreambooth can turn your text into images. Like, show me Shrek and Batman making out. There you go. These pictures are never perfect, but sometimes they're quite nice. I should totally learn how these models work, because they're getting bigger as we speak. There are already models which can make film instead of images. Maybe someday we'll make movies or even video games just by describing them to a computer. The mere existence of these models makes generative adversarial networks suddenly less impressive. But I want to talk about my generative adversarial network anyway, so here we go. Here at OIST, I've been working on a machine learning project which can take hours or days to process, even on the local supercomputers. So while it's processing, I use the spare time working on my own machine learning projects, or just playing FTL Multiverse. My latest personal machine learning project has been another generative adversarial network, or GAN for short. I've made these models before, but I've never been completely satisfied, so I'm trying again. In past videos about GANs, I've described them using Animal Crossing characters.
When you're sure they won't remember any of this in the morning, you show them some of your fake art and say, "Hey, look at all this totally authentic art I found." Your donor says, "That's a fake. Here's how I can tell." You make some more fake art and try again, and eventually your donor says, "Yep, that looks like real art to me." In the morning, when the hangover wears off, you offload your improved fakes onto the donor, and they naively bring them to the museum. Once more, the curator separates your fakes from the real deal, and once more the donor learns to tell the difference. If you do this for a while, you and the donor improve enough that your fake art starts looking pretty good. And remember, you've still never seen real art. You've improved by learning to trick someone who's learning alongside you. This is my understanding of a generative adversarial network.
Yeah, past Ted, that's pretty much spot on. To summarize, a generator makes random seeds into fake images. The discriminator gets images and guesses if they're fake or legitimate. The generator learns to make better fakes by watching how the discriminator identifies them. The battle between generator and discriminator is why it's called adversarial. If you want to make big images, like 1024 by 1024, a regular GAN won't cut it. You'll need a progressive GAN, which starts making small images and progresses to make bigger and bigger images. I've described these using more Animal Crossing characters.
Red has a dog, and the villager has a dog. Red and the villager don't actually interact at all. Their dogs play together in their daily walks. Okay, so Red is telling his dog how to make art by shaking its leash a little, and the other dog describes that art to the villager by tugging its leash a little. This metaphor is weird, okay? I'm trying, jeez. Red has a kid, and Red's kid has a puppy. Red has 2 leashes now, one on his dog, one on his kid. He can shake one leash, and his dog makes art. He can shake the other leash, and his kid shakes his leash, so his puppy makes art too. Red's kid and his puppy have natural talent, making more complicated art, but they aren't good at art yet. So Red and his dog upscale their own art to help them out. The villager has a kid too, and the villager's kid has a puppy also. The villager's kid and his puppy have natural talent for inspecting more complicated art, but they aren't good at art yet. So the villager and his dog downsample art to interpret it alongside them. As the kids and puppies grow up, their parents and their dogs let them handle more and more of the art, until eventually the parents let their dogs go into the wild and just shake their kids' leashes instead. Someday the kids can have their own kids with their own puppies, and so on. The successors can handle higher resolution and more detail because they're linked to their ancestors, basically. Isn't that wild?
As weird as this description is, it's pretty accurate. Except, I didn't realize back then, Red and the villager only have one dog each. Their kids don't get new dogs. They're sharing the same dog. My goal with generative adversarial networks has always been making fake Pokemon from these pins. I call the generated ones Blorpomon because they're always kind of blorpy. Last time I made a progressive GAN, I noticed the Blorpomon were always generated the same color. So the main reason for this video is that I found a solution to this color collapse. To share the solution, I'll have to describe mini batches. A model is usually trained one batch at a time. The model is given some data, it operates on that data, and its outputs are compared to real answers using a loss function to find a loss. The model learns to decrease this loss with backpropagation. Then the model is given another batch of data to do this again. But a discriminator is meant to be trained with two mini batches. It's given real images and fake images separately, and the two losses are added together. That way, the discriminator can consider not just each image individually, but the whole mini-batch. For example, maybe a GAN's generator generates only green Blorpomon. If the discriminator figures out the green ones are fake, the generator can just switch colors and make purple Blorpomon. But if the generator considers the entire mini-batch, it can say, yeah, these look like Pokemon, but they're all the same color, and real Pokemon come in all kinds of colors. This must be a mini batch of fakes. So the discriminator ain't fooled, and switching colors won't work. The generator has to learn some variety. So let's check out a model I made in PyTorch. By the way, this is available on GitHub. I don't do that enough. First, in the file utils.py, I have a bunch of parameters. For example, we can make GANs generate MNIST digits, Blorpomon, or human faces. And we can make them grayscale or in color. I also choose to train 5 discriminators at once, so the generator can learn from all 5 of them. I don't know if that's a good idea or not, but whatever. Some parameters are a dictionary of parameters because making things too complicated is how I roll. For example, this one is the generator's learning rate, which can be different for each level of progressive training. If the level is the integer 0, the generator makes 4x4 images. If the level is the integer 1, the generator makes 8x8 images. If the level is a non-integer between 0 and 1, the generator makes 8x8 images by combining a 4x4 image and an 8x8 image. This freeze parameter can make it so old layers stop training when we progress to new levels. So any variable which starts args dot comes from right here. Utils.py also defines some plotting functions and buffers which can spill out images. Anyway, the generator's first layer is seed in. It turns a batch of seed-sized tensors into something large enough to make 4x4 shapes. The generator's last layer is image out, which makes its input into images. This layer uses convolution and self-attention from a package called Torghgan, which can implement attention, dense layers, residual layers, and a whole lot more. Check it out. Between seed in and image out, there are 4 layers which I call expanders. Each expander doubles the size of its input after feeding it through a convolutional layer, or a residual block, or whatever. I just commented lines out to test stuff because I don't want to add more parameters. So, when the generator is called to make an image, it checks the level it's on. If the level is an integer, it includes every expander up to that level number. If the level isn't an integer, it includes every expander up to that level number rounded down to make an old image. Then it includes the next expander to make a new image. The final image is a combination of the old image and the new image scaled up. The discriminator's first layer is stats_in, which accepts a whole bunch of statistics regarding each individual image and the entire mini-batch. For example, it can see the average value of one image's greenness, how green is the image, and it can compare that to the whole mini-batch's average greenness. The discriminator also has a layer called image_in, which turns the mini-batch of images into a big tensor. The last layer is pred_out, which predicts if each image in the mini-batch is a legitimate one or a fake. Between these layers are 4 layers, which I call contractors. Each contractor shrinks the size of its input after some convolution. So, if the discriminator is called to judge some images, it checks the level it's on. If the level is an integer, it includes that many contractors, starting from the back. If the level isn't an integer, it first uses image_in on the input and a shrunken down version of the input. The larger output goes through the new contractor and is combined with the smaller output. So that's pretty complicated, but it works. Check this out. I started with the MNIST digits. These here are real handwritten numbers. It's hard to tell because they're 4x4. But these are fake digits. They look pretty good because a 4x4 image is easy to fake. Down here we can see the loss values each epoch for the generator and the discriminators. And over here we can see how accurate the discriminators are on real images and fake images. Looks like they have trouble telling them apart. Each time the level changes, there's a vertical line. So right now the images are moving from 4x4 to 8x8. Let's speed it up until we have 32x32 pictures. Those look like digits. In another video, I showed it's better to fake MNIST digits with classification, so the generator is specifically told to make like a 3, say. But these look fine. Now let's try human faces. First, let's try without compression, beginning at 32x32 images. Well, actually, these look pretty good. They look just about as good as they look when I make them with progression. 32x32 is still a pretty small image size, I guess. My GPU is too small to work with 1024x1024 images. So let's try progressing Blorbomon. Well, they look pretty simple and empty, sort of faceless. But I suppose that makes sense. Human faces have lots of traits in common, but Pokemon faces are all over the place, and I only have a few hundred of them. At least I'm satisfied with the variety. These aren't limited to one color at all. Here's another animation. I saved the generator every once in a while, so I can show you how each generator uses the same seed as the seed changes continuously. There are way better generative adversarial networks out there, but I'm not trying to make the best one ever, I'm just learning. One thing I've learned? Even the best image generators make mistakes. If you play with a text-to-image model like Craiyon for a while, you'll notice it can't, for example, make upside-down pyramids, which should be pretty easy. They're also not great with hands.
Matt, that's your new album?
Yeah, with a lot more fingers. A lot more fingers, but it gets the level of my arm hair. It's a little bit shy. Yeah, it's a little light on it, but still.
Humans have trouble drawing hands too. Hands are infamously difficult to draw. Not even our own brains are good with hands. One technique to have a lucid dream, to realize that you're dreaming while you're asleep, is to count your fingers. If you have 5 fingers, you're awake. But if you're dreaming, you might be missing a finger, or you might have more fingers than usual. So, to end this video with something completely unrelated, Have you seen any videos or memes about the backrooms? It's sort of a popular horror concept, where someone might just disappear because they phase through reality and end up in a surreal, repetitive environment, sometimes with monsters. Lots of people make content about backrooms, and lots of people speculate about the meaning or the lore of that content. I'm not saying this is the secret backstory revealed, but personally I think the backrooms look like something computer-generated, or maybe generated in the sleeping mind. Maybe someone phasing through reality is entering a strange cognitive state in their imagination. The backrooms might look legitimate at first, but like computer-generated images, they don't hold up to scrutiny. I'm still working on a project involving Friston's free energy principle, but I don't think it'll be ready to talk about for quite a while, so maybe next month's video will just be me playing FTL Multiverse. Bye-bye.
By the way, I've got a Patreon at patreon.com/thinkster. I want to thank all these squidlings and elder squids. Thanks.